Lovastatin, and also known as Mevacor, and explain how it lowers cholesterol by targeting a key step in cholesterol biosynthesis. So we'll start by briefly reviewing how cholesterol is made in the body, then discuss the specific enzyme Lovastatin inhibits, how the drug becomes active, and why this matters clinically. So what is Lovastatin? Lovastatin is a drug developed by Merck and belongs to the statin family. Statins are among the most widely prescribed medications worldwide for lowering cholesterol. Lovastatin works by inhibiting cholesterol synthesis in the liver. High cholesterol, especially elevated LDL cholesterol, increases the risk of atherosclerosis, heart attacks, and strokes. So by lowering the LDL values, Lovastatin helps reduce cardiovascular risk as a whole. But to also understand how this works, we first need to look at how cholesterol is produced in the body. Cholesterol biosynthesis pathway. Cholesterol is synthesized primarily in the liver from acetyl-CoA. The pathway begins with acetyl-CoA molecules combining to form HMG-CoA. The key regulatory step occurs when HMG-CoA is converted into mevalonate. This reaction is catalyzed by the enzyme HMG-CoA reductase. This step is critical because it is the rate-limiting and highly regulated step in cholesterol biosynthesis. After mevalonate is formed, several additional steps ultimately lead to cholesterol production. The key enzyme HMG-CoA reductase. HMG-CoA reductase is the central control point of cholesterol synthesis. It converts HMG-CoA into mevalonate using NADPH as a reducing agent. This is used because of the rate-limiting step. Controlling this enzyme directly controls cholesterol production. This enzyme is tightly regulated by the body through feedback inhibition, hormonal control, and lastly, changes in gene expression. And this is exactly where Lovastatin acts on. How Lovastatin works. Lovastatin inhibits HMG-CoA reductase by acting as a competitive inhibitor. Importantly, Lovastatin is actually administered as an inactive lactone form, meaning it is pro-drug. Once inside the body, especially in the liver, the lactone ring is hydrolyzed to form the active B-hydroxy acid form. This active form structurally resembles mevalonate, the natural product of the HMG-CoA reductase reaction. Because of this similarity, Lovastatin binds to the active site of HMG-CoA reductase and blocks access of the HMG-CoA. By inhibiting this step, Lovastatin reduces mevalonate production, which ultimately decreases cholesterol synthesis. As cholesterol levels fall in the liver compensates by increasing LDL receptor expression, pulling more LDL cholesterol out of the bloodstream, and this is how blood LDL levels will decrease as a whole. The primary benefit of Lovastatin is lowering LDL cholesterol, often called bad cholesterol. By lowering LDL levels, Lovastatin reduces plaque formation in arteries and decreases the risk of cardiovascular events such as heart attacks and strokes. Statins, like Lovastatin, are among the most well-studied and widely used medications in preventive cardiology. Because they target a specific rate-limiting enzyme, they are both effective and mechanically precise. Conclusion. To conclude, Lovastatin lowers cholesterol by inhibiting HMG-CoA reductase, the key rate-limiting enzyme in cholesterol biosynthesis. It is administered as a prodrug and converted to its active B-hydroxy acid form in the liver. By blocking mevalonate formation, it reduces cholesterol production and increases LDL clearance from the blood. Overall, Lovastatin is a powerful example of how understanding biochemical pathways allow us to design targeted therapies that improve human health. Thank you. And on the next slide, these are the citations of the paper.